Consider the instruments behind your face. Every sunset, every painting, every shade you have ever named is built entirely from mixing signals from exactly 3 kinds of color receptor. Down in the warm shallows of the world's reefs lives a predator no bigger than your finger, yet packed into its eyes, which are smaller than a grain of rice, are up to 16 distinct types of light-sensing cell. These receptors are tuned to slices of the spectrum far beyond human limits, reaching deep into the ultraviolet and out into the far red. They detect bands of light that to us are simply an absence, perceiving colors that have no name in any human language. You would logically assume an animal carrying this much visual machinery perceives a world of staggering richness. With a 16 receptor array, they should be able to split apart shades so close together that we would swear they were identical. But when researchers in Australia trained these animals to associate specific colors with food and then slowly narrowed the gap between the shades, the animals began to fail. The threshold at which they could no longer tell 2 colors apart was surprisingly wide. A human eye can distinguish wavelengths just a few nanometers apart, but the mantis shrimp needed the colors to be separated by massive gaps before it could see any difference at all. Evolution built the most heavily engineered photoreceptors on Earth, only to make the animal objectively worse at discriminating color than a creature with exactly 3. Human eyes work by comparison. Your brain weighs the ratio between receptors to compute a precise shade. It takes crucial neural time. The mantis shrimp bypasses this. Its color channels fire in a rapid, linear pattern, never pausing to merge. It operates like a barcode scanner. As an object crosses its field of view, each receptor simply registers a yes or no response to a specific wavelength, logging the signature of the thing passing by in sequence. By skipping the math, the animal trades subtle color resolution for raw processing velocity. It offloads heavy computation from its tiny brain directly to the physical structures of the eyes. The complexity of this visual system is designed for speed, turning perception from a tool of appreciation into a mechanism for instant categorization. That speed is a biological necessity, because folded beneath its head, the mantis shrimp conceals a spring-loaded, saddle-shaped club held tightly under tension. When the latch releases, the club accelerates like a bullet, reaching its target in a fraction of a millisecond and tearing the water apart. The physical strike is so fast that the water in front of the club boils. This creates a cavitation bubble of vapor that collapses in on itself with a flash of heat and a snap of sound, hitting the prey a second time with the concussive force of the collapsing water. Wielding a physical weapon at this velocity requires a targeting system that operates instantaneously. A brain that pauses to admire the exact shade of a target belongs to a dead animal. The coarse barcode vision is a survival requirement. In the high-speed chaos of a predatory reef environment, hesitating to analyze fine color ratios would mean missing a meal or becoming one. As light travels through the water, it can twist and spiral, turning like a screw as it moves. This animation shows what physicists call circular polarization. To nearly every creature that has ever lived, this spiraling light is completely invisible. The mantis shrimp reads it natively. It is the only known animal on Earth capable of detecting and sorting this spiraling light without the aid of instruments. Specific patches on the mantis shrimp's body naturally reflect this circularly polarized light, creating a visual signal invisible to the rest of the ocean. These reflective patches form an encrypted communication network. They allow the shrimp to signal a mate or warn a rival using visual codes that pass entirely unseen by the larger predators hunting nearby. They exploited a loophole in the physics of light, ensuring their survival by operating on a visual frequency isolated from the rest of the ecosystem. Engineers in laboratories are now reverse engineering these layered polarization sensors to build new camera technology. This imaging display shows how the technology applies to medicine. Healthy tissue and diseased tissue reflect polarized light slightly differently. While the sample on the left looks normal to standard cameras, the polarization filter on the right reveals a sharply glowing tumor mass. By mimicking the crustacean's biological filters, these cameras can spot the earliest shadow of cancer long before standard medical imaging or a human surgeon's eye can detect it. Sensors modeled on the structure of these eyes now allow us to detect anomalies that were previously invisible, providing a new way to look inside the human body. We live in a visual world that is rich, slow, and precise. The mantis shrimp patrols a reality that is fast, coarse, and threaded with spiraling light we will never witness. We tend to assume that there is a single objective reality out there, and that seeing better simply means seeing more of it. But there is no single world. There is only the specific reality each creature is biologically built to perceive to survive. The 16 receptor eyes of the mantis shrimp prove that nature does not engineer for aesthetic perfection or human ideals of beauty. It builds for the ruthless, beautiful efficiency of staying alive.